Welcome back. I hope you were able to do this problem as a review. One of the hints I gave you is that we're going to be using one of the derivatives of Dalton's law. Now, in this problem, you'll notice that they give you the grams of nitrogen and also, let's write here, 4 grams. They also give you the 7 grams of CO2 of carbon dioxide. And they do give you other pieces of information. They tell us that they're in this, it's a mixture, so they're in the same container, so they both have the same volume. And if they're in the same container, they also have the same temperature. Now remember, we can't use Celsius, so I'm going to go ahead and change this already. This will be 273 Kelvin. Now, there are multiple ways of doing this. But what we got to do first is we got to change the grams to moles, okay? We're going to need to probably use, and if you recall, one of the ideal gas law formulas is to solve for pressure. And if you divide 4 grams, the molar mass of nitrogen is 14.01, but it's diatomic, so times 2 would make it 28.02 grams per mole, and that will give us 0.143 moles of nitrogen. For carbon dioxide, we have 7 grams, and if you do the molar mass of carbon dioxide, carbon is 12.01, and then oxygen is 16 times 2, which is 32. If you add that with 12.01, you get a molar mass of 44.01 grams per mole, and in moles that will give us 0.159 moles. Okay, now we have the moles of each. Okay, if you want, they do want the partial pressure of each gas, and they also want the total. Well, what we could do is we could do this twice for each gas and then add it up, and that will work. That is one option. In fact, I'll go ahead and do that as well, okay? If you get, let's say, let's go ahead and solve it for nitrogen. So let's go here to the next page here. And let's say we were finding the component of nitrogen. Well, we just saw that the moles of nitrogen was 0.143 moles. Now remember that R is always a constant, 0.0821 liter atmospheres over mole Kelvin. And then your temperature is 273. And then, of course, we're dividing by the volume, which is 15. Okay, so let's go ahead and do that. All right. And if you do that, you will get, when you do the math, you're going to get a partial pressure of nitrogen. It should come out to 0.214. Now, there's a quick way that I'm going to show you something. There's a quick way to do this. You see, every problem has this part the same. This is the RTV components. If you multiply RTV, you will get, if you plug in the numbers, 1.494. Okay? And if you notice, if you multiply the 1.494 by the 0.143 over here, you're going to get this number here. That's the partial pressure of nitrogen. Now, the reason I'm showing you this is because let's do the same thing with CO2. Okay? The moles of CO2 is different. The moles of CO2 is 0.159 moles. But this part, RTV, is the same. Okay? Because they're in the same container. So if you multiply that by 1.494, you're going to get a partial pressure of CO2 equal to 0.238 ATMs. Now, if we were to add these two numbers, you would also get the total. So adding these two, and I'm going to show you how we can go full circle. Adding the two gives you a total pressure of 0.451 ATMs. Now, another thing that we could have done, and I'm going to show you how we get this same number, is multiply this with the total moles, okay? And I'll show you what I mean. If you get the total moles and you solve for the total pressure, let me put here N. I'm sorry about that. Let's put here NTRTV. Well, we already know the total moles. If you add 0.143 over here and you add the 0.159, the total moles is let me see where I wrote that here. 0.302. And if we multiply it by this piece here, which we already know is the 1.494, you will get the same answer, which is 0.451 ATMs as your total. The beauty of this is that there's many ways to do this. You could even do mole fractions and find the partial pressures of each. So this is one of those problems that there are multiple ways of solving it. Okay? So that was the answer to this question. All right, moving forward. Now comes the difficult part. How do we measure when a gas is collected over water? Okay? Here you're looking at a device. There's a reaction going on in the test tube where zinc and hydrochloric acid are reacting down here. Okay? And as they react, one of the things that happens, this is a single replacement reaction, you're going to be making hydrogen gas. Okay? You're also going to be making zinc chloride, but you're making hydrogen gas. And that hydrogen gas is going through here, and it's being collected in here. Now, notice it's being collected over water. So here's the thing. When you measure the pressure in this container, the pressure in there is not just the pressure due to hydrogen gas, as you can see here. There's also some pressure due to water. So in this container, there's actually two gases. So the pressure of the container is not just the hydrogen you're collecting, it's the pressure of the hydrogen plus the pressure of some water vapor that's in there. So you have a mixture. Now, when you're using this technique, what we care about is the pressure of the gas you're collecting. You don't care about the water. In fact, here's how you eliminate the pressure of the water. What you do is you get the total pressure and you use Dalton's law. The total pressure minus the pressure of the water will give you the pressure of what you want. Okay? This is an adjustment that we need to make when we're collecting gases over water. You have to subtract the pressure due to water. Now, if you're wondering, how do we know that number? Well, good news is the number will be given to you. Okay? Here's a table. Now, here they're in millimeters of mercury. You could easily change that to torrs. Well, in torrs, it's the same. You could change it to kilopascals or ATMs. This table happens to be in millimeters of mercury. And the table tells you what the vapor pressure is of water. So this will be the vapor pressure of water at these specific temperatures. Okay? So the problem will tell you. If the question is at 22 degrees Celsius, which is not on this table, they will give you the value, which obviously will be somewhere in there. Now, notice this relationship. Notice that as temperature increases, the vapor pressure of water also increases. It's temperature dependent. The hotter it is, the more water becomes a gas. And the more gas that you have, the greater the vapor pressure. So that is a direct correlation between temperature and an increase in vapor pressure. Okay? And when we say vapor pressure, we're basically talking about the pressure of water as a gas. Okay? So that is going to be given to you in the question. All right. So let's see if we can put this together. We have a question here. You have solid potassium chlorate. It's being heated in a test tube, just like that picture you saw. Except we're not making hydrogen, we're making potassium chloride, and here is the gas we're making. We're making oxygen gas. So, the oxygen is being produced and collected by the displacement of water method. It's being collected the same way you saw in the picture. And the temperature of that water that it's being collected in is 22 degrees Celsius. They also give you the total pressure. Be careful. We don't want the total pressure. You see, the total pressure, which is atmospheric pressure or total pressure, will be the pressure of the oxygen you're collecting plus some of that pressure is due to water. We need to subtract this number. This is the one we want to use, not this one. So if you keep reading, it tells you that the volume is given, it's collected. The volume collected was 0.650 liters. And here it is. This is what I was telling you. At 22 degrees Celsius, they tell you that the vapor pressure of water is 21 torrs. Now, in a minute, we're going to go ahead and do that. What do they want us to do? They want us to find first the partial pressure of oxygen. Let's do that first, okay? So we can do that right here in this page. Let me erase this for a minute, and I'm going to go ahead and do that part for you. So we know that the total pressure plus or equals the pressure of the oxygen plus the water, plus the pressure of the water. We know that they're equal to each other. The sum of the two adds up to the total. Well, what we want is the pressure of oxygen. So how do we do that? We get the total pressure minus the pressure of the water, and that difference will give us the pressure of the oxygen. Now, the good thing is that they're both in torrs. The total pressure is 754 torrs minus 21 torrs. When you subtract these two numbers, the difference will be the pressure of just the oxygen. So this is the number that we need. Okay? Now, let's continue. That's just the first part of the question. Here is what they want. Now that we know the partial pressure of oxygen, they want to know what mass of potassium chlorate decomposes. This becomes a stoichiometry problem. Take a look at this. What is the given? We just found out that we know the partial pressure of oxygen. Okay? It's 733 torrs. We just found that out. What we're looking for is the mass of potassium chlorate. This is what we call a mass to, this is going to be a non-STP problem where we're going to be going from oxygen to potassium chlorate. We're going to look for the mass of potassium chlorate. Now, I'm going to show you what we got to do. We have the ideal gas law. This formula is very useful. What we're going to do is, in stoichiometry, the first thing you do is you always solve for moles. So if you set this up, remember, N is going to be equal to PV over RT. Okay? Now, if you recall from before, we were given the temperatures 22 degrees Celsius. We got to change that to Kelvin. We have the volume, and we also have the pressure. Be careful, you're going to use the pressure of the oxygen, not the total pressure. We don't care about the total pressure because the stoichiometry is specifically between oxygen and KClO3. So let's do some conversions here before we start. First thing we got to do is let's get that temperature and add 273. That will get us to 295 Kelvin. Okay. The pressure needs to be changed. It is in torrs. If you recall, 1 atm is what we need to change it to. Is equal to 760 torrs. So we'll go ahead and divide that, and you're going to get 0.992 atms. And fortunately for us, the volume is already in liters. It's 0.650 liters. Okay, so here's what we got to do. Let's plug in the numbers into the ideal gas law equation. So the moles is going to be the 0.964, and that's going to be ATMs. Okay, we just got that from, oh, you know what? I apologize. I put the wrong number here. I apologize. If you divide by 760, it's not 0.992. It's 0.964. Okay, so I apologize for that. I wrote it correctly down here. Okay, so it's 0.964. So fix that. And then we got our volume. Okay, all I'm doing is substituting it into this equation here, which is 0.650 liters. And then remember R is a constant, 0.0821. That will be liter atmospheres over, let me fix that. Lack of space over here. There we go. And then we got over here the temperature at 295. Now, when you do the math, you'll notice the ATMs cancel, the liters cancel, so do the Kelvin. We're left with moles. And the moles that you get is 0.0259. Now, be careful. This is just moles of oxygen. We don't care about oxygen. We want potassium chlorate. So, we got to do stoichiometry. This would be moles of A. How do we go from A to B? Well, the mole ratio, B over A, okay, is 2 over 3. Okay, 2 moles of KClO3 over 3 moles of oxygen. So it's 2 moles, 2 over 3. When you do the math here, you get 0.01725, and this is going to be moles of KClO3. Now we're in business. This is the guy we want, but we don't want moles. We want the mass. So we're going to have to find the mass of KClO3. Now remember, when you're finding molar mass, never use coefficients. Okay, let me give myself a little bit of room over here. The potassium is 39.10. Okay, and chlorine is 35.45. And then you got oxygen, which is 3 times 16. That's 48. When you add that up, your molar mass is 122.55 grams per mole. So to go from moles to mass, you're going to multiply the moles by the molar mass, which is 122.55. Okay? And that's grams per mole. The moles will cancel. And we're going to round our number to 3 significant digits. And when you do the math here, you get 2.11 grams of KClO3, and that would be your final answer. Now, what makes this problem more difficult is you're doing everything the same. Just be very careful. I almost messed up when I wrote the pressure here. You don't want the total pressure. That's really the only adjustment, which is going back to this. You want to subtract the pressure due to water, because the equation, the gas you're collecting of interest is oxygen. So once you subtract the pressure of water from the total, which ended up being 733 torrs, that's the actual pressure due to oxygen. Had you used 754, you would have used a wrong pressure. And that's why these problems get to be a little bit tricky. So that's really the only adjustment. Everything else is the same. Make sure that temperatures in Kelvin, volumes in liters, okay, pressures in ATMs. We had to change torrs to ATMs. But once you do that, you get this and you're good, okay? So again, when you look at one of these problems here, you'll notice that when you're collecting a gas over water, just remember that the pressure that's measured here, which is probably what they're going to give you in the problem, is referred to as the total pressure. It's always going to be some pressure of something you're collecting. In this case, we were collecting oxygen in our problem. And there's always going to be some pressure due to water. In this example, the gas that's being collected is hydrogen gas. And that's represented here because hydrogen's diatomic. So keep that in mind. Okay? And I believe that's it for this lesson. Thank you.